Okay. We study RLC circuit. So RLC circuit are resistor, L inductance, and C is capacitor. So circuit equation for RLC circuit is closely related to the solution of quadratic equation. So we return to middle school to find the solution of the quadratic equation. In general, a quadratic equation is this kind of form. We have a polynomial and the highest order is x squared. To make this one to be non-negligible, we need to choose a is non-zero. So we assume that these three numbers are real numbers. But by the way, we have a number line. The x, a real number x, depends on the choice of the origin. That's a very important point. So we can shift the origin to another place to simplify the expression. So that is called the translation. So and sometimes we can magnify a variable, or sometimes we can shift a variable by shifting the origin to another. So even though it is a rather complicated to solve this problem, but we can always shift the variable to find an easier problem. And actually by translation, we can do this. First of all, let us consider the case, if it is possible, to reduce this equation into a very simple form. Difference of the square of two numbers is always factorized. The middle school students know how to factorize this as a sum and difference of a linear function. So using this, once you can decompose into equals 0, the solution is quite simple to obtain. And I believe that everybody in our class knows it very well. But let me review. So first of all, because A is non-zero, so we just scale out the over factor by dividing both sides by A. Then we obtain this kind of form in general. So I don't like this because I want to use an elementary factorization rule. So first, I can define this one to make a completing the square. So x squared plus 2 beta, where 2 beta equals b over a. And gamma is c over a. Okay, that's fine. So introduction of this additional factor of 2 is to make use of the expansion formula. If you expand x plus beta, we have always a factor of 2. Combinatoric factor, the binomial coefficient. Okay, so we make use of this to kill this linear term. How? This is called completing the square. So subtract this one, that you will find this guy. So this guy is simply expressed as sum of x and shifted value square subtracted by this shifted value. As a result, any quadratic function has vanishing linear term with appropriate translation. That is called completing the square. So we shift origin by beta, then this one becomes a new real number. So y equals x plus beta. And then we use the factorization formula to find the y should be minus delta or plus delta, because we know that any product real number becomes 0 only if either one is a zero. If both of them are non-zero, it is impossible to have zero. So that's every elementary student knows. Finally, we have obtained the value for plus minus delta and shift the value by beta to return to the original solution, x. You know how to determine this delta. This delta is nothing but this expression, but what happens if I have this delta to be square root of something? So when the inside the square root, if it is positive, that's fine. But if it is negative, we have some problem. That's the reason that will give an imaginary number. So we say this beta squared minus alpha is a discriminant. So if the discriminant is a positive, then we would have two real solution. And if the discriminant is negative, then we would have two complex number, and those two complex numbers are complex conjugate. So everybody knows very well about this expression. So this guy that determines whether the inside the square root is a positive or negative, so we call it discriminant. And the two solutions are always expressed as a complex conjugate. Let us consider the potential equation of RLC circuit. This is the potential applied to the inductor, resistor, and capacitor. So we find the current is the derivative of charge saved inside a capacitor, and always the two places of a capacitor has the opposite sign. The direction of I is chosen so that the positive charge is charged on this plate. So if I grows, I enters, and I is being emitted from some other plate, so we choose the charge Q, not here, but here. You should be careful about the sign. Anyway, I is the first order derivative of the charge. Therefore, first order derivative I is the second order derivative of Q. And this guy is the first order derivative of Q. So we have this kind of form. This is a generalized form of the simple harmonic oscillator. Simple harmonic oscillator is x double dot something x equals 0. However, we have additional piece that depends on the velocity. In that case, we say it is a kind of damped harmonic oscillator because the first order derivative interferes the motion by damping force that is applied opposite to the velocity. So this circuit equation is a very mathematically, these two equations are equivalent. Physically, is an absolutely different nature. What we want to do is to apply the method of this elementary method of simplifying the quadratic equation. We just make use of the same method to simplify this differential equation that has the first order derivative into an equation scaled with some exponential function and then multiplied by a solution that is much simpler than the original solution, original equation. That's what I'm going to study today. So let's see if it is possible to reduce this equation into this kind of form. Let us record the Leibniz rule for the derivative of product. If I apply the derivative many times, then this derivative is assured by two factors. It's something like the binomial expansion. So we have two terms powered by the exponent n, then we need to find the multiplicity of the term carrying a's kth power and b's n minus kth power, that is n factorial, for the whole permutation. However, k powers of a are all indistinguishable, so we have to divide it by the double counted numbers, and this also gives a double counted cases. If I remove these multiplicities, the final multiplicity, distinguishable multiplicities in the expanded terms will be like that. Something like that, this derivative applies either A or B. Therefore, this kind of power is replaced with the derivative applied to a factor of A and applied to a factor of B. That's called the Leibniz rule. So I'd like to, this is the answer, but I'd like to introduce an exponential function to shift the scale to remove the current term. So first of all, exponential lambda t multiplied by y, I take the derivative, then exponential's derivative and y's derivative. So one by one. The single derivative do not have multiplicity factor. It is just a single. And I replace this time derivative with y dot, and exponential function gives a parameter lambda only and still alive after the derivative. So lambda t, exponential lambda t is factor dot. Similar manner, I can take the double derivative to find that now we have multiplicity factor appears for the single derivative, and after rearranging the expressions, we have this kind of piece. And then we substitute all of these rescaled results into the original equation. These three terms, and combine them. There is a double derivative. Aha, I can find there are two terms carrying the first order piece. And this is the original term, and this lambda dependent term appears. So if I look at this term, I can find a value of lambda that kills the first order derivative. So I realized that the solution of lambda is that. So that value can be substituted in here to simplify the remaining constant piece. The result is this. Finally, this expression is identical to this factor. Now lambda is found to be this guy, so lambda has been substituted, and we have y double derivative and constant multiplied by y equals 0. We know, everybody knows that exponential function never becomes 0. Never, never, never. Therefore, this equals 0 is equivalent to this equals 0. What's better? It's simpler to solve than this. And you don't have to memorize the solution table. You can derive everything. And this kind of thing, you can do the job very easily. We know how to solve this equation. For example, critically damped motion, this one becomes a 0. But usually there is no explanation how to solve the critically damped solution. But This one, even high school students know how to solve this. Okay? If it is positive, a simple harmonic oscillator with e to the I omega t plus e to the minus I omega t, C1, C2, something like that, where omega equals the square root of this guy. Okay? What happens if they are upside down? I mean, this guy is greater than this guy. Then damping force is very strong. Therefore, in that case, we have only exponentially growing or decaying function. So in that case, the sign is flipped in comparison with the frequency omega, and it shows the decaying over-damped solution, and this is an under-damped solution. Sure, there is overfactor that decays exponentially. Okay,